Hello friends, I'm back again with the ARM exploitation series. In this series, basically, we are going to quickly discuss how to bypass the stack NX bit uh, protection. So the NX bit, or the non-executable bit, is basically a bit that's set by the microprocessor or the CPU for every page and memory access. What it means is basically when the CPU tries to execute an instruction, it checks basically a bit that has been activated, which indicates if this specific page has constructions that can be either read, written, or can be executed. So usually stack and heap is marked as non-executable, which means that if you try to use a simple stack overflow from the earlier video that we had seen and sort of provided the shellcode, it would not work. What would happen is that the kernel would panic, and at that point of time, it would indicate that it's bypassing the protection of the kernel, and that way it will basically halt the program. So I'll quickly show you what I mean by that. Let's take GDB exploit again. Quick note that the no-op instruction in ARM assembly is basically all zeros. What that means is basically, if you are familiar with x86, the no-op instruction in hexadecimal language is /x90. However, in ARM exploits, it's /x00/x00, which means that you cannot actually use any sort of knobs that are supposed to be used for knob/sled payload, which is a way of a technique of sort of doing exploitation on x86. So let's put a breakpoint again at the same address that we had done in the last video. Now let's run the program. We have BB, CCC, DDD, HHH, actually EEE, and HHH. Alright, so let's look at the stack pointer. And as you can see that we are going to override the program counter with 48, 48, 48. Observe that there are 0, 0, 0, 0, 0, 0 sort of hexadecimal values right after that. If you did an x/I and looked at SP plus 8, it's indicating that it's and equals R0, 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 which is what your no-op instruction in ARM is. So what I'm going to do is I'm going to set the variable value of the program counter with the value of your stack pointer's value. So technically, if the stack was executable, at that point of time it would have tried to execute this instruction. However, we'll observe that we cannot actually execute this instruction set. So what I'm going to do is quickly set the value for demonstration purposes for 0x 2f d f f8 6c to 0x 2f df f870. Let's observe the stack now. As you can see that I have overwritten the value of the program counter with 2f df f870, which means that it should point to the no ops instruction right after that value. Let's do a step. And as you can see that it indicates that the program has received a signal execution bad access, and it does not access the memory. It says kernel protection failure, which sort of indicates that there is a protection of NX bit being set on the stack, and that does not allow you to execute sort of an instruction on the stack. So how do we bypass this? There are a couple of methods. There is a method called return-oriented programming, which I'll try to cover up in a later video. Basically, in this case, what we are going to try to do is use a return to LibC technique. A return to LibC technique is an old technique where basically you bypass this method of protecting by using an XBit by calling system functions and providing the right values to it. Usually this is useful for very small exploitation scenarios. For example, the scenario would be where the user wants to do a local exploit and set the UID to 0. That would allow basically the user to become a super user using this executable. So that is sort of the intended function where you can pass the right values to set UID, and when the program returns, it should return back with a shell. So we would have to change the functions of doing a set UID and then a system/bin/sh, so that way you basically get a root shell on that specific machine using a local exploit. In this case, since I'm already root, I'm not going to try to do a set UID. What I plan to do is execute some simple functions like ls or something similar and see if I can execute that. So let's do that again. As I had mentioned earlier, that this both the heap and the stack as well as the library functions are randomized, so their base addresses are randomized every time you reboot your iPad. So at this point of time, what I'm planning to do is to use this system variables functions value. So the address for system function is 37C49814. Let's observe one quick caveat about this instance. One thing that ARM processors support is that they support two different types of languages. One is the ARM assembly, one is the thumb assembly. The ARM assembly is 32-bit assembly language, however the thumb is a 16-bit assembly language. So if you look at the system address, you will observe that however this does not look like an ARM assembly. The reason I'm saying that is based on these two instructions. If you look at it, it seems like ARM assembly is more of a thumb assembly, where basically the opcodes are basically 16 bytes long as opposed to 32 bytes long. So that is a problem, because it seems like the binaries for the LibC function have been compiled with thumb instruction set as opposed to an assembly instruction set. However, a good solution for this is basically there is a register called CPSR. It's a control status register that tells the microprocessor or the ARM processor in this case which kind of languages should it use when it tries to execute the instruction. The way to activate this instruction for thumb assembly is basically add a 1 at the end of the address that you're trying to execute. And basically for thumb assemblies, the last 3 bits basically act as like status bits. So if you in this case the address for system is 37C49814, we basically add +1, which makes it 15, and that basically changes the last bit to 1, which indicates to the microprocessor or ARM processor that it's supposed to execute in thumb assembly mode. So in this case we are going to use that. So let's try that. What I plan to do at this point of time is call first an exit function, just to show that we can execute the return to libc functionality. So the execute function just has 37C3D9 D0. One thing that I also want to point out is that as I mentioned, the arguments in case of ARM assembly need to be pushed into the registers. Now the system function technically only takes one argument, which is the command that needs to be executed, and this needs to be pushed onto into R0. Now the good part for this simple demo program that we have is that if you look at the R0 instruction, you will observe that it has a value 414141. Recall from the earlier time when we had passed the values, the 414141 corresponds to hexadecimal 41, which in ASCII table set as the A character, and basically that was the first character that we had passed on. So it seems like R0 is already pointing to a part of our, or actually to the starting part of our exploitation string. So in this case it would be really easy to exploit this program, because we can pass the command in as the first part of the exploitation string and then the address of system, and that should help us to execute the necessary command. Alright, so getting back to the quick demonstration. What I plan to do is exit out of this program. Recall I'm not again using GDB because of the fact that I'm using gets. I need to provide the gets with my values, so it's easier to do it using printf. So this is the address that we had observed, and what I plan to do is pass on the exploit with exit. And if you just call exploit, if you did a printf exploit, observe that it says this is the normal flow. However, if you do this, it does a segmentation fault. Let's quickly look why did it do that. I'm gonna quickly look at the exploit. Do a breakpoint at 2f24. And then run. Let's look at the exit address. So it's C3D9D0. Oh, that is the reason that we can observe that it didn't work, because the address was wrong. Exit out of program, do a print. This time it has C3D9D1 exploit, and we basically executed the exit function. So now what I plan to do is also exploit this by calling the ls-ltr function. In this case, the system's address is 37C498D15. Let's see if this address now works. And it does. However, you will see that there's a segmentation fault. Basically, when system tries to exit, at that point of time, since there is no exit address that has been provided correctly, it ends up causing a segmentation fault. However, it does execute the instructions that we wanted. We can also try with other pointers. So observe that, as I had said, if you have the right command at the beginning of the exploit string and the right address for system, in this case which has been increased by +1 for compensating for the thumb assembly programming, it seems like that we can execute it. What I plan to do now is try to use this to call some other function. I'm just making sure that we have the right number of character sets so that it's perfect. And now what I plan to do is call the pwd function just to see if things work correctly for us. There you go, and it says that it's /variable/root, which is what the value, which is what the current pwd for us is as well. So this sort of helps us to bypass the stack executable protection, which does not allow the stack to execute any addresses. Any instructions, and thus Retn to LibC helps us to bypass sort of the NX bit protection instantiated by the operating system. That's pretty much it, folks. In the next section, we will discuss the ASLR and how to bypass that for a local exploit in this case. Thank you.